Good morning. Welcome back. Um, Before we get started with the lecture, just want to get a feedback from the class in terms of the exam. Any comments? How do you feel?
Better.
That's good. Again, that's not the case for all of you. I was wondering, because if you think about the exam, after you took the exam, you look at the true-or-false questions, the last 6 were part of the homework. So if you work in the homework, you should saw those that were there. The first 5 were part of the 6, lecture 6 and 7, which was basically definitions from the most important concepts. So true or false questions, half of them were part of the homework, the other half came straight from the lecture. The problems, so we worked on the end method in class. I thought having you just work on a couple of the spaces in the tableau will make things easier. Same thing for the two-phase method. And then the last 2 questions, the third question was basically discussed in class. The only thing I did was to change the name of the company. But if you look at the problem, it will be an example that we work in class. Same questions, same answers. And the last problem of the exam was in the homework. It was one of the review problems, so I didn't have time to complete it in class, so what I did was I put it in the exam. But it was in the homework. So if you work in the homework, and you went through the notes, you didn't have any problems working with the exam. I already graded the exams, have the grades with me. What I noticed is half of you improve your scores and half of you decrease your scores. So for those of you who did better, that's good news. That said that you're catching the material and you're understanding the material. For those of you that decrease your scores, I would like to talk to you. If you want to stop by my office, we can discuss the exam and then try to find out what's not working for you. Okay? So I'm open to your suggestions, so we can talk one-on-one if you like. Okay? But again, try to make my exam as fair as possible. So again, if you go through the review process of going through the lectures, the homework, should be you clarify your questions, you should be doing well in the exams. Okay? Any questions, comments? Okay, so we're gonna leave the exam discussion for the end of the class. So one topic that we didn't have the time to complete before the exam was the optimal analysis, and this is part of the dual theory. So what we're going to do is complete this lecture, and then we're going to transition to the new topic, which is one of the most important applications for operational research and linear program, the transportation problem. But before we go to that topic, let's just finish this topic. And I don't know if you remember the last lecture or the last topic we covered was dual theory, dual analysis, and we talked about the importance of the dual in terms of finding ways to improve the solution times for your problem. So if you have a problem with a lot of constraints, you know that is not good for the simplex method because it's going to take more time to complete the solution or to get a solution using the simplex method because you have a lot of constraints. So you can change that to a problem in which you have more variables and few constraints. That will accelerate the time that you will have in order to solve the problem. So that's one of several advantages of having the dual problem. Also, it helps you to analyze the shadow prices and to make decisions, managerial decisions in terms of how to allocate your resources. So if you solve the dual, you know that you're going to get as a solution, what you're going to get is your dual price. So that will give you an idea of how expensive are your resources, and also will help you make decisions on how to allocate the time that you have or the capacity that you have for those resources. Okay, so the last topic for this lecture is the post-optimal analysis. And we went through part of this part of the lecture already. So we deal with the sensitivity of the optimal solution. That was on the previous lecture. We determine the range for different LP parameters that will keep the optimal basic variables unchanged. So you know if you change the capacity of your resources, you'll keep the optimal solution the same for some specific range of the problem or your capacities. If you're using the computer, please shut down the monitor. In this lecture, we deal with making changes in the parameters of the model and finding the new optimal solution. So we talked about this problem. This is a problem that we have discussed already. So this is a toy company. We have 3 operations, and we want to determine how many products of each type we want to produce. So we want to maximize in order to increase our revenue, and we have a capacity limitation for each operation. So for the post-optimal analysis, we discussed the importance of understanding which ones were our starting variables. And in the optimal tableau, we want to capture, or we want to find out where that identity matrix for the initial tableau was, because the place where the identity matrix was is going to let us know where the new inverse matrix is, and that inverse matrix is what we're going to use for our post-optimal analysis. So the last problem of the exam basically asks you to use this inverse. And part in the second method, you need to use that inverse matrix to find out your answer. So we discussed the dual. So we found the dual problem for this TOEIC production planning problem. And we discussed the changes affecting feasibility. So if the feasibility of the current optimal solution is affected only if the right-hand side of the constraint is changed. And this change requires recomputing the right-hand side of the tableau using this formula. So what we do is we multiply the inverse in iteration I. So the inverse again is this matrix, which is located where the identity matrix was at the beginning of the solution of the simplex method. So we use the inverse, and we multiply the inverse times the new right-hand side of the constraint. So if we change the capacity of our resources, and we want to find out what is the new right-hand side of the tableau, then we just multiply the new right-hand side of the constraints times the inverse. Recall that the right-hand side of the tableau gives the values of the basic variables. Okay, so this is something that we already discussed. So we went through these examples to discuss the feasibility of the problem. And for the first case, we found that the problem remained feasible, and the associated revenue is changed to 1,880. And for the second situation, we found that the problem was infeasible because we found that the right-hand side, the new right-hand side, was negative for one of the variables. Now what we're going to discuss is changes affecting optimality. So again, the first thing we discussed was the changes affecting the feasibility. So do you remember what feasibility means? Problem is feasible, if you can find a solution. It is unfeasible if there's no solution for the problem. So when you look at the constraints of your problem, if the problem is infeasible, that means that there's no solution that satisfies all the constraints. But if it is feasible, that means that at least one solution exists that can satisfy all the constraints. So now what we want to look at is changes affecting optimality. So that means that we know that we're going to have an optimal solution for our problem. If we make changes to the problem and we keep the same solution, that means that the solution remains optimal. But if we make changes to the problem and we get a different solution, that means that we are making changes to the optimality solution or the optimal solution that we already found. So consider making changes in the objective coefficient. So we're going to look at the objective function of the problem. These changes affect only the optimality of the solution and require computing the zero coefficients, the reduced cost, according to the following procedure. So compute the dual values and then substitute the new dual values to determine the new reduced cost. So let me just explain that with an example. So in this situation, again, we refer back to the TOEIC model. Suppose that the company has a new pricing policy to meet the competition. The unit revenues are 2, 3, and 4 for train, trucks, and car tours respectively. So what we're going to do is, you know what the revenue is in our problem, right? The revenue is in the objective function. So we are trying to maximize our revenue by deciding how many units we're going to produce. So now the situation is basically saying we're going to change the revenue that we're going to make for each product. So for the first product it's $2 now, for the second product it's $3, and for the third product it's $4. And we want to see if that making that change in the revenue affect the solution that we have already, which is optimal. So the new objective function is, again, we are maximizing our revenue. Z equals 2x1 plus 3x2 plus 4x3. And this is coming from here. So those are the new coefficients for our objective function because we are making changes in the revenue for each product. So using method number 2 to obtain dual values, we find that y1, y2, and y3 equals 3, 4, 0 times, this is the inverse from the optimal solution in the tableau, and this is one of the methods we discussed to find the dual values from the optimal tableau from the primal. So the dual values are 3 over 2, 5 over 4, and 0. So we found the duals. The objective 0 computations in any simplex iteration the objective
equation coefficient or the reduced cost of xj is computed as follows. So that now we want to compute or recompute the objective 0. So for the primal, so this is primal z equation, coefficients of xi will be equal to the left hand side of the J dual constraint minus the right hand side of the J dual constraint. Something to remember is that we don't have to compute those for the basic variables because they are always 0. So we only have to compute the reduced cost for those that are not basic. So it is not necessary to compute the objective row coefficients of the basic variables because they are always 0. So for the non-basic, we have the reduced cost equals of x1 equals y1 plus 3y2 plus y3 minus 2. And if you substitute the values of y1, y2, and y3, then you will get that the reduced cost is 13/4. Then the reduced cost of x4, which is our next non-basic, is y1 minus 0, which is 3/2. And the reduced cost of x5 equals y2 minus 0 equals 5/2. So the current solution remains optimal because they are all greater than 0. Yes, sir.
What constraints are you referencing?
These are the dual constraints. This is our original problem. Check back. Okay. Got it?
Constraint 1 has constraint 2 is basic variable.
Yes, sir. Any other question? Okay. And hopefully after this lecture, I know you guys, this is involved a lot of things that comes together into a particular problem, so you need to be aware of all the concepts. Hopefully, I'm pretty sure after this lecture, the topics are going to become more practical in terms of more practical examples. We're not going to be looking at the solution methods, which is what we have been doing so far. What we are doing in this lecture is basically, you know how to formulate a problem. Now this is the solution method. This is how you can modify your problem and get other solutions based on the dual. But after our discussion of the dual theory, then we're going to start looking at more applied practical problems, such as the transportation problems. And we're going to see how the transportation problem is very useful and so on. So let's try to understand. Again, what I'm saying is this is very important. You need to understand what is the dual, how you find the dual, how can you modify your problem and still keep the solution that you have, because that will give you a better idea of how to manage your resources. So this is very powerful, but we're going to transition to more practical problems after this lecture. So suppose now the total objective function is changed to this new objective function. Now we're going to perform. So the question will be, this should be, sorry about that, this should be, will the optimum solution change? So we're going to perform the same steps. We start with, we have y1, y2, and y3. So these are 3, 4, and 0 times the inverse, which is coming from the primal optimal solution. And this is 3 over 2, 5 over 4, and 0. Now we're going to compute the reduced cost for each non-basic. So if we compute the reduced cost for x1, this will be y1 plus 3y2 plus y3 minus 6. And this is 3 over 2 plus 3 times 5 over 4 plus 0 minus 6, and this is minus 3, 4. Right there, you'll see that the new reduced cost is negative, so that makes the solution it's not optimal. Okay, so this is negative, so that will affect the current optimality of the problem. So the new reduced cost of x1 shows that the current solution is not optimal. And you can come, if you make that change, you see that the current solution is not optimal. There's a method that I mentioned earlier that is called the simplex dual, that you can take that information at this point of the tableau, and you can find the optimal solution for those p values. But again, those are more advanced topics, and if you are interested, again, Dr. Novoa is going to be teaching a second part of this course. So I encourage you, if you are interested in these type of topics, that go and take that class. And also, if you are, for instance, if you are thinking big in the future, if you want to be a consultant or something like that, these tools will be very helpful. If you're interested, you can always talk to me afterwards. So, and also it's very good stuff if you're interested in doing research, going to graduate school and do research and maybe be a professor or faculty in the future. This is something also that you can explore. So that will basically conclude the topic, the dual theory topic, in which we define the dual problem, the primal-dual relationship, the economic interpretation of duality, and the post-optimal analysis of the dual. Let's transition to the new topic. Which is, again, this is more practical, more application type of topic. You're going to look at the transportation and the assignment problems. And this is material that is in part coming from your textbook, chapter 5. And this is, again, going back to formulation. You remember one of the first things we did in this class was to formulate several types of problems. But I also mentioned at that point that you can come up with some recipes. If you identify this problem looks like this, you can usually take the formulation, a general formulation, and apply it to that problem. One of those recipes, calling them recipes, is the transportation problem, because it's a very general format that you can apply to multiple problems, not only transportation but other applications. So if you understand the problem, if you understand how it's formulated, again, you're going to have some supply, some demand, you can use that recipe and you can apply it to different applications. Transportation model is very important, it's very useful, especially in logistics. Companies such as Walmart, HEB, UPS, Dell, all those companies that are involved with shipping something, transportation problem is very useful because you want to be able to move your product as efficient as possible, paying the less money that you need to pay to increase your revenues. Okay, but the transportation problem will involve different things such as the time it takes to run truck from point A to point B, the cost of moving that truck, and so on. So in this class,
This lecture, we're going to study the transportation and the assignment problem. And we're going to consider only a few items that affect the problem. We're not going to add a lot of detail. We're basically going to focus on the cost that takes to move one or particular vehicle from one point to another point in the map. Okay, so transportation problem and the assignment problem. Okay, so again, I've been showing this slide a lot at the beginning of each lecture. So these are the course objectives, and we are basically at the last bullet: recognize, analyze, formulate, and solve industrial problems that can deal with linear programming. Two of those problems are the transportation and the assignment problem. Okay, so the learning objectives is to discuss two special types of linear program: transportation and the assignment problem. And these are the recommended readings from your textbook. So 5.1 and 5.4. In the agenda, definition of the transportation problem. We're going to discuss what does it means to have a balanced transportation problem and the assignment model. Okay, so a general description. Transportation problems deals with the problem of finding the best way to fulfill the demand of end demand points. So you have multiple clients, different points in the state, and you want to fulfill those demands. You have your warehouse located here in San Marcos. You want to find the best way to ship your product to your clients and spend the less money that you can spend. Okay, so you want to minimize your cost. You see the capacities of your end supply points. So usually, if you are a big company, you have multiple supply points. Let's say you are worldwide, so you will have supply in Europe, supply in North America, supply in South America, and you want to ship to different countries. You need to find out which supply point will cost you less to supply a specific client. Okay, so you have end demand points and supply points. Generally, a variable cost of shipping the product from one supply point to a demand point is taken into consideration. So there will be some costs involved. There will be transportation costs, maybe type of transportation that you're using, or maybe it is the time it will take you to take the product to a particular location. So there will be some penalty if you don't deliver on time, so you need to take that into account as well. So there's multiple things. Again, we're going to focus only on the transportation cost, but those other details can be added to the model easily. So instead of discussing a transportation or vehicle type of problem, decided to start with a different type of problem to show you that even though it's a transportation problem, usually you think about vehicles, trucks, airplanes, and so on. You can also apply that same format or same transportation model to other applications such as the power generation. So usually what you have is a generation plant, and you want to supply your electricity to different points in the network. So residential consumers, you also have commercial industries, and you want to know which generation plant or power station should supply that particular point in the network. So the example refers to this company called Power Corporation, and has 3 electric power plants that supply the electric needs for 4 cities. The associated supply of each plant and demand of each city is given in table 1. So this is the table. You have 3 plants, and you have a supply for each plant. So plant 1 can supply 35 million kilowatt.
So this is for plant 1. Plant 2 can supply 50, and plant 3 can supply 40. Okay, those are the capacities you have for each plant. Now, the associated supply of each plant and demand of each city is here again. So the demand for each city is listed on the bottom. So city 1 requires 45 million kilowatts, city 2, city 3, and city 4. So you have 3 plants producing this power, and you have 4 cities that depend on those plants for their supply. You also have some costs. The cost of sending 1 million kilowatts of electricity from a plant to a city depends on the distance the electricity must travel. So if you supply 1 million kilowatts to city number 1 from plant 1, this is your cost in million, and so on. So you have a cost from point A to point B. So plant 1 to city number 2 is 6 million, plant 1 to city 3, and so on. So this matrix is basically giving you the cost for moving that electricity from this plant to this city. Any questions? Do you understand what the problem is, what you're trying to do with this problem, right? You're supplying, and you want to satisfy the demand for your plant. Okay? So, the transportation problem is specified by the supply, the demand, and the shipping costs. The relevant data can be summarized in the transportation tableau, and the transportation tableau implicitly expresses the supply and the demand constraints and the shipping cost between each demand and supply point. So that tableau is what you saw on the previous slide. So you have the demand, you have the supply for each source, and you have the cost from one point to another. And this is the transportation tableau again. This is what I show you on slide 8. Are you able to finish your notes? Okay. Okay, so now what we're going to do is we're going to formulate this problem. And you're going to help me formulate this problem. So, let me see if I have a marker here. Okay, so anyone knows how can you define the decision variable for this problem? Any guess? So you're trying, yes. The plans are already stated, those are fixed. You know how many you have, you know how many clients you have. What is the question you're trying to answer? You have your plans, you have your customers. No? Yeah, the decision variable is xij, but I want you to tell me what xij is going to be. What's the meaning of xij? Correct. That's the question you want to answer. You want to know how much you're going to send from plant I to customer J. Okay, so xij is the amount of electricity produced at plant I and sent to city J. So if you have x14, that means that your decision variable is the amount of electricity produced at plant 1 and sent to city 4. So amount of electricity produce at plant 1 and sent to city 4. Okay, does that make sense? And so every time that you're trying to define a decision variable, what you do is you ask yourself, what is the question you want to answer with this problem? In this case, we want to know how much you're going to send from a plant to a city. Okay, so the objective function, so to minimize the total cost of shipping from plants to city, so we have 3 plants, 4 cities, so we need to define our objective function based on those, so we know our decision variables. I believe you don't have this table in your slide, but it's the same table I showed previously. So I added here just to make it easier for you to see how to write the objective function. So what you're going to do is you're going to take each item in the tableau and you're going to state a decision variable for that item and make it part of the objective function. So for the first, you know that it's going to take, or it's going to cost you $8 to go from plant 1 to city 1. And then it's going to cost you $6 to go from plant 1 to city 2. It's going to cost you $10 to go from plant 1 to city 3. And it's going to cost you $9 to go from 1 to 4. Now you have to do the same for plant 2. So you have plus 9 to 1. You go from plant 2 to city number 1. Then plus 12 x to 2 and plus 13 x to 3 plus 7 x to 4. So we did this one, this one, this one, this one, this one. Then we have plus 14x 31 plus 9x 32 plus 16x 33 plus 5x 34. So you want to minimize the cost of supplying your demand. You know the cost, so you want to minimize that cost. Okay, so the solution should give you the amount that plant 1 is going to supply to each city. It's going to be the one that is more cost effective. Questions about the objective function. So again, every time you see a problem that can be formulated as a transportation problem, this is how you're going to formulate the objective function. Okay, so you look at the cost, you know the cities, the supply, the demand, formulate your objective function. Now, we're going to have some supply constraints. So since each supply point has a limited production capacity, we need to provide a constraint to limit that production capacity. So we know that for plant 1, the capacity is 35, plant 2 is 50, and plant 3 is 40. So we're going to use that information to formulate the constraint for the supply. Anyone want to try to write one of the constraints for a bonus point? And I can have 2. If you want, try there and have someone else here. There's no markers.
And I will add that point to the current exam. This is exam number 2. So I mean, it's worth it if you want to try.
And you cannot cheat because the constraints are in 16.
Okay.
Yeah.
So that's the flat.
So you're gonna have a constraint for each plant,
Yeah.
basically. So you know that that plant can only supply this amount. So you're gonna be doing the first one, which is for plant 1. So at least you know that it has to be less than or equal to 35. Yes. You want to try it?
Well, I don't know. I want to make sure that I'm on the right track as to what I can give my team. So you're implementing the XID rule in the constraints as well?
Yeah.
Plan? Okay, got that.
Yeah. Okay. So I can try to incorporate for the second plant, but I don't have any extra markers. I don't know what happened. I used to have a lot of them here. You can write it in your paper and then
I'll try the demand.
Demand, yeah. You'll wait for the next one.
This represents.
Or just X2, X2.
I mean, you can help each other. That's okay. I'll come up with the right constraint. So remember, xi is the plant, j is the customer. So if you're writing constraint for a plant, your I should stay the same.
So would this be for plant 2?
So, yeah, but you don't have to specify the cost because the costs are going to be okay. So it will be this.
Okay.
Would this be for demand? Or demand just
Yes. So for the demand, instead of being 10%, we'll make greater.
Oh, yeah.
Okay, good.
So, yeah, that's right.
Just double check so you have 2, 3.
1, 1, 1. 2, 2, 2, 2. Yeah, yeah. So that's correct. So, so since all of you were helping, I'll give you a point to all of you. So that will be part of your second exam. But the idea is that you're going to have the constraint, at least for the supply, you're going to have the constraint for each plant. And you know that your capacity is limited, so it's going to be less than or equal to that capacity. So let me write that in here. It is x11 plus x12 plus x13 plus x14 less than or equal to 35, x21 plus x22 plus x23 plus x24 less than or equal to 50, x31 plus x32 plus x33, 34 less than or equal to 40. So this is plant 1, 2, and 3. Okay. And for the demand then, it's just the, if you look at the tableau, you're basically going this direction, like x11, x12, x13, x14, less than 35. Same here, same here. Those are the 3 constraints. Now, if you are going to look at the demand, then instead of going in this direction, you're going this direction. So you're going to have a supply from plant 1, supply from plant 2, supply from plant 3 to city 1. So
You're going to have X11, so that means that plant 1 is going to supply city 1. Then X21, plant 2 is going to supply city 1, plus X31. Same for this is city 1. Then 1, 2 plus X22 plus X32. X13 plus X23 plus X33. X14 plus X24 plus X34. So this is city 1, city 2, city 3, and city 4. Okay, so there's something missing here. So this is 45, this is 20, this is 30, and this is 30.
what do you think about the sign of those constraints? And what sign are you going to use here? And why?
Well, you more than that.
Yes. So that means that that constraint cannot be less than, because if you put less than, that means that you can satisfy that constraint by supplying less than what is required. But if you put a greater or equal constraint, you know that the minimum that you're going to be supplying is the requirement. If you go over that, that's okay, but you want to supply at least what is required by the customer.
So this will be greater or equal. And that only applies to this particular problem.
For other problems, you want to use a equal constraint here, because you want to supply only what is required. Yes.
Is the sum of your supply the sum of your demand always going to be each other?
There. What do you mean by?
Like 45, 20, 30, 30.
Oh yes, that's a good question. This, if you add this, 60, 80, 125, then you have 125. This is because the problem is balanced. So demand is equal to the supply. But that's not always the case. You can have an unbalanced problem, and we're going to discuss what to do when those problems arise. But usually if you have more supply than demand, that's not a problem. But if you have less supply than demand, then you're going to incur an extra cost for not being able to supply that particular demand.
Okay, so I'm going backwards. So the last constraint is the time constraint, so you know all your variables needs to be greater or equal to 0.
And then again, here's the formulation, the complete problem formulation. So that's for your reference. So this is what we just did. Okay, let's look at now another problem which is related to the distribution of cars. So MG Auto has 3 plants in Los Angeles, Detroit, and New Orleans, and 2 major distribution centers in Denver and Miami. The quarterly capacities of the three plants are 1,000, 1,500, and 1,200 cars. And the demands of the two distribution centers are for the same period are this one, 2,300 and 1,400. Here I have two pieces of information. This sample is coming from your textbook. So the millage chart and the transportation cost per car between the plants and distribution centers are here. Here you see the millage to go from Los Angeles to Denver, and again from Detroit to Denver, New Orleans to Denver, and from Los Angeles to Miami, and so on. And what we do usually is we put a cost to the distance. So you can see how these distances translate into cost. So if you're going to travel more distance, then you're going to have a larger cost for using that distribution center. Same here, you know that the longest distance is from Los Angeles to Miami, so you will see that there's a large cost when compared to these two for that distance. So the larger the distance, the larger the cost. So that's the information we have for the problem. Another way to see these problems is using what we call a network. So you have this nodes, arcs, and another set of nodes. This first group of nodes basically represent the sources. These case are your plants. And this group of nodes are the destination, which are your distribution centers. So you're going to have an arc going from each node to another node, basically meaning that you can move from this plant to this distribution center, from this plant to this distribution center, and so on. And each arc will have a cost, which we call a C, and is basically tied to a decision variable. So we're going to talk more about networks in this course by the end of the semester, but this is just giving you an idea of how you can represent these problems using a network. Okay, so let's work with the formulation really quick. So we're going to use the same concepts we used for the first example. So we're going to use the cost to formulate our objective function. So again, we have a cost representing each point 1 from supply to demand. So I'm going to use x11, and you can see the numbers here. So that means that you go from Los Angeles to Denver, and you have a cost of 80. Then you have 215 to go from Los Angeles to Miami, and then 100 to go from Detroit to Denver, and then 108 to go from Detroit to Miami, and then 102 to go from New Orleans to Denver, and finally 68 to go from New Orleans to Miami. Okay, so now we need to state our supply constraints and our demand constraints. So same way, we have x11 plus x12 equals 1,000, and this is for Los Angeles. Then we have x21 plus x22 equal 1,500. So this is Detroit. And then we have x31 plus x32 equals
1200, and this is New Orleans. So these are our supplies. Now we're gonna formulate the constraint for the demand. So we have x11 plus x21 plus x31 equals 2300, and this is for Denver, and x12 plus x22 plus x32 equal 1400, and this is Miami. And the non-negativity constraints. So xij should be greater than 0 for I equal 1, 2, and 3, and j equals 1 and 2. Okay. So for those of you who are interested, again, this is a extra assignment, and I'll give you another point. For exam 2, if you solve the problem with the solver, so you can submit that by tomorrow. I'm gonna make a link in the crack site, and if you submit your solution, you can upload the solution, and I'll give you that point.
It was Torah, or was the
Solver, the Excel solver. Yes. Okay. How much time still have? So let me, because I want to use some time to discuss the exam. So the general description of the transportation problem, again, you have set up n supply points from which a good is shipped. Supply point I can supply at most is units, and set up n demand point which the good is shipped. The demand point J must receive at least DI units of the shipped goods, and each unit produces a supply point I and shipped to demand point J incurs a variable cost, Cij. So every, let me go back here, you're able to get those SI unit, DI units, and cost, Cij. So every transportation problem will have this structure. So you have one decision variable in terms of Xij. You will have a constraint, an objective function in which you are minimizing your cost, and you're doing the summation of the cost times the decision variable, and you have some constraint for the supply and some constraint for the demand. That's all you have. So if I ask you to formulate a transportation problem, this is what I'm expecting to see. Your decision variable, Sij, your objective function, and your constraints for the demand and the supply and demand. That's all. Okay? So one more thing, just to go and pass the exams. So here are some of the companies that always are looking for people trained in logistics, transportation model optimization, HEB, Walmart, UPS. So if you click, let me see if I can. Here. No, that's bad. taking longer than expected. Okay, for instance, if you look at HEB, they have a transportation division, and they have a couple of opportunities in that particular area. I was searching for same thing for Walmart. You will see that they have a logistic division, UPS, and so on. So again, as I mentioned earlier, you see those tools help you find a job in these companies that basically do mostly logistics and product shipment and so on. Okay, so I'll stop here. I'm gonna pass the exams. Again, I was